Sir, yes, sir.
Yes, sir.
So hope you have enjoyed this 2 class break actually after examination. Now we need to restart our subject again. But you will feel a difference as compared to before examination and after examination. So before examination, what was our objective was actually we have gone very slow. So main objective was to create, you can say, liking or curiosity, your curiosity in a subject transport phenomena. So we are not worried about information or syllabus content before examination. Just we have gone very slow. But now, because we have limited time, so we need to complete the syllabus by the end of say mid of April or third week of April. So we have very limited time left. So hereafter you will see that okay, the lectures will be full of information and this thing syllabus. So you need to catch up with speed and hope you have prepared well for mid-sem exam. If you prepared well, certainly you can catch up with the speed what way I am going with all this thing, because this background is very, very important. Whatever we have covered before, that is very, very important. So today we are going to start this equation of change. This is also called as the equation of motion. So this is equation of change or equation of motion. This topic we are going to start. This is there in chapter 3 in BSL. Okay, so what is the difference? And this already we have covered in chapter 2 shell balance approach. We will call it as a simplified method. Simplified method to get the velocity profile and flux profile. So that already we have covered. So generally this simplified method is easier for use when we have one dimensional flow. Flow is in one direction only and variation is in one direction. There is no multi-dimensional variation and multi-dimensional flow. So then we have 1D flow and variation only in one direction. That time we can go for simplified shell balance approach. And how we have solved the problem? Given the problem, we have take out all the information, then add the assumption. Then with this simplified information, with simplified information with all assumption, we have applied the shell balance for 1D problem and 1D variation. So certainly we'll get a simple differential equation. So we'll get a differential equation and that can be solved easily to get the velocity profile and flux profile. This is what we have done in previous case. We'll call it as a simplified method. So equation of change, you can say a generalized version of this simplified method. So there it is not a different than shell balance approach. This is the generalized approach. So what generalized approach means? Most importantly, why we are studying this equation of change, so it can handle any problem. So if I have multi-dimensional flow with multi-dimensional variation, so we can handle using this equation of change. So what is equation of change? Without thinking the problem, we will take a shell balance. Without thinking the problem is, we'll think that there are all three velocities, say for Cartesian coordinates x, y, z, and they are varying in all three directions and unsteady flow. So we'll apply the shell balance and get the generalized differential equation. So this after applying the shell balance for generalize all three-dimensional variation, unsteady flow. So whatever be the differential equation at the end we'll get, that is called as the equation of change. So this is also shell balance, but generalized shell balance equation. So once we have this, so we can add all the information and this thing and solve to get the velocity profile and flux profile. So we know that, okay, if I have 1D variation and one directional variation, 1D flow, so it needs at least two boundary conditions. So as we go for complex conditions, so it will be multi-dimensional, multi-velocity profile. So it will be complicated actually. So it will not be so easy to solve. So that is what we will see. So then if say your problem is very complicated and analytical solutions are not available, that is why equation of change, sometimes people will solve using numerical methods, and which itself is one area of study, and that is called as a computational fluid dynamics. That is nothing but the solving equation of change using numerical methods. So that we are going to see equation of change in this class. So not in this class. So before starting equation of change, we need some additional information. So equation of continuity, we have used this equation of continuity couple of times. So today we'll discuss this equation of continuity, and then we'll discuss equation of motion. So we'll start with equation of continuity, and then we'll move on to equation of motion discussion actually. And as usual, what we are doing is, so before discussing anything, whatever with the mathematical operators and everything involved in the discussion will be properly explained, so that you will get the mathematics and its importance. So what is the importance of mathematics is, so if you have complex equation, so writing that complex equation into simplified form, that is what the, you can say, use of mathematics in our transport phenomena subjects. So you should not lost in the equation. So complex equation will be there. So you should not lost in the equation. You should be concentrating more on physics of the problem and apply whatever mathematical techniques you have learned before. Already you have learned most of the mathematical techniques, that you can use it here, so that a complex mathematical equation can be rewritten in a simplified form, which can be understood, which can be written very easily. So for that, we'll discuss whatever be the mathematical operators which will come across in this discussion, equation of continuity and equation of motion. So different types of derivatives. So there are different types of derivative actually. So this different types of derivatives. So you might have heard of total derivatives and partial time derivatives. So we'll introduce one more type of derivative, that is called as substantial time derivatives. So what is this partial time derivatives? So excellent example is given in a book. So I will go with same example. So this partial time derivative is variation of concentration with respect to time at constant location xyz, at constant location xyz. So you consider a pond. Okay, there is a very big pond. Say maybe say you consider Ambazari Lake, and consider that there is a platform which is inside the pond. A steady platform is there inside the pond, and you are holding a transparent cube of 1 meter by 1 meter by 1 meter, and you are standing on this steady platform and inside the pond, and you are measuring the fish concentration. Concentration, and fish can move easily in whatever be the your control volume. So it can move in the control volume, it can move out in the control volume very easily inside the pond, but this location of cube remains constant with respect to location. This location of this cube is not changing, and you are measuring the concentration of fish, variation of concentration with respect to time only. This small t represent time. So if that measurement is called as a partial time derivatives, because you are measuring just with respect to time, keeping all other parameter constant. Generally, currently, physically, there are 4 dimensions. 3 are a geometric dimension, and 4th dimension is time. So I am measuring with respect to time, keeping xyz constant. Hence, it is called as a partial time derivative. So this is a time derivative, but it is partial. That is called as the partial time derivative. Now, second case. Now, say you have hired a submarine. So you have hired the submarine, and now you are moving in XYZ direction with the speed of submarine. So you can change the speed of submarine. It depends upon you. What speed you want to maintain in X direction, what speed you want to maintain in Y direction, what speed you want to maintain in Z direction. And if you are measuring again the concentration of fish in same cubical control volume, then it is called as the total time derivatives. So total time derivative dc by dt will be equals to partial time derivative with respect to time, plus this will be the velocity of your submarine, okay, in X direction. This will be velocity of submarine in X direction, dc by dx, partial dc by dx, plus this will be the velocity of your submarine in Y direction, and this will be the velocity of your submarine in Z direction, and you are measuring, again you are measuring the concentration of fishes in your control volume, okay, with respect to time. So you are moving also, and you are measuring the concentration of fish. Such a measurement is called as a total time derivative. So you are moving in XYZ direction also, and you are measuring the concentration of it. This is called as the total time derivative. And third type of derivatives is actually substantial time derivative. This is, you can say, again one step ahead version of total time derivative. Now you are not on submarine, so you cannot control this velocity. You are on a molecule of the pond itself. You are on a molecule of the pond itself, and you are moving with the pond velocity itself. Whatever be the velocity of molecule of the pond in x direction, you are moving with that velocity. Whatever be the velocity of pond molecule in y direction, you are moving with that velocity. And whatever be the velocity of pond velocity in z direction, you are moving in that xyz direction with a molecule. You are not giving any force to move in xyz direction and measuring again number of pieces in your control volume. Such a measurement is called as substantial time derivative, that is represented by capital D by dt. Okay, this is substantial time derivative, capital D by dt of property concentration. So that will be equals to, this will be partial with respect to time, and this will be the velocity of this pond molecule, velocity of pond molecule in x direction. This will be velocity of pond molecule in y direction. This will be velocity of pond molecule in z direction. And this is again variation of concentration in x direction, variation of concentration in z direction. So you are measuring the concentration of fishes in the control volume in all three cases. In all three cases, you have fixed the control volume. Okay, control volume is there. So in that control volume, you are measuring the concentration of fishes. In first case, location is constant. In second case, you are moving in XYZ direction with your velocity. Okay, so you can set this velocity. So say submarine, you can move in X direction, you can move in Y direction, you can control this velocity. In third, you are moving with the molecules of pond itself. You are moving with a pond velocity, X velocity, pond Y velocity, pond Z velocity. So this is partial time derivative, this is total time derivative, and this is substantial time derivative. So this operator we are going to use in our discussion here when we will be discussing equation of continuity and equation of change, actually equation of motion. So these three derivatives are clear to everybody. This is very important actually. So as I am telling, why we are discussing this is, so instead of writing this much big equation, so we can write this small, capital D dc by dt. So total time derivative, which will be defined like this. Okay, substantial time derivative, capital D by dt. So which will be defined like this. This we are going to use many times actually, substantial time derivative. This you are well aware. Okay, partial derivative, total derivative. So partial time derivative here. So this denominator is time here, and this is total time derivative here. These are, you are already aware actually, aware of this thing actually. And this is the only new operator we have introduced, substantial time derivative. So here velocity is velocity of the pond. Here velocity, we are controlling the velocity. This is clear to everybody? Darshan, roll number 70, Darshan.
Yes, sir.
Clear, na?
Yes, sir. Yes, sir.
Okay. So with this brief information, so we can move on more mathematical operators. So, but I am repeating this again and again because a transport phenomena looks very complicated. Why? Because most of the time student will give more concentration in mathematics involved in transport phenomena. So, and they will not use the mathematics they already learn, and they will forget about physics. Then transport phenomena is a nightmare for you actually. So you should not lose your attention from the physics of the transport phenomena, fundamentals of the transport phenomena, and mathematics you should use as a tool to discuss transport phenomena easily. That is what. Hence, I am not going details in mathematics. So wherever, whichever operator is important, that operator only I am discussing. And maybe at the end, we'll compile everything and we'll sum up all the mathematics involved in transport phenomena. So this is del operator. So already some of the properties of the del operator we have discussed when we were discussing generalized Newton's law of viscosity. If you remember, there some of the properties of the del operator, del dot, del into, that already we have discussed. So we'll just revise that property once again, and then so this is what generalized Newton's law of viscosity. Here we have discussed del into V, del dot V, and this is del operator for Cartesian coordinate system. This is the definition of del operator for Cartesian coordinate system, where this delta is a conical delta. Okay, 1, 2, 3 represent a direction. Okay, 1, 2, 3 represent direction. So this will be x, y, z, or x1, x2, x3, or anything. And this will be a del operator for cylindrical coordinate system r, theta, and z. And this will be a del operator, definition of del operator for spherical coordinate system r, theta, and phi. Okay, so this is the definition of del operator, and this is how del dot is defined. Del dot, a vector. Del dot vector equals to variation of vector x vector with respect to x plus variation of y vector with respect to y plus variation of z vector with respect to z. Here we are discussing velocity. So del dot velocity will be equals to variation of x velocity with respect to x plus variation of y velocity with respect to y plus variation of z velocity, and this is termed as del dot v. Then del into v, this is called as a divergence. Okay, not dot product. This is called as a divergence also. This is a dot product, and this is the scalar product. Okay, del v, del. This is also called as a del into v. This is called as a del dot v. So this will be a variation of one velocity, one dimensional velocity with respect to another, ij. Okay, ij. So this will be del vj, del vi. It all depends upon the suffix of which velocity we are discussing, and this transport will be exactly opposite. Okay, del variation of vi velocity with respect to xj. Okay, del x in another direction. So this ij represent based on this suffix of del and vector. Actually, it will be given, and accordingly you can get del into v. So this is the del operator. So this is called as a scalar multiplication, del into. So this is the scalar multiplication. That we have discussed this vector multiplication. This is the vector multiplication, dot multiplication with vector actually. Okay, this is a dot multiplication, del into v with respect to vector. Similarly, if there is a scalar, okay, scalar will not have any direction. Okay, so this will be a del of del x of s plus this will be y, del s by del y plus del s by del z, and this is called as a scalar multiplication of del operator, and it is called as a del into. This is called as a del into scalar. So this will be operated like this. Okay, so you should note down and remember, and you can revise your mathematics which you have covered. And this del operator operates similar to a differential operator. This is also kind of a differential operator only. So all other properties are similar to a differential operator, but this is del operator, del into. Then this is called as a vector multiplication of a del operator, vector multiplication. Okay, vector multiplication, and this is this represent as a cross, del cross vx. This will be cross multiplication, cross product, del cross x. So you if say this is del cross v, and with respect to x, so this you remember this cycle. This is x, y, z, and this is reverse of y and z. Okay, so this is x, y, z, and this is y, z. So this del cross v with respect to x will be equals to del by del I of vz minus del by del z of vy. Similarly, same cycle is xyz. So this is del cross v pi, y, z, x. Cycle is same, y, z. This is x, y, z, then y, z, x, then z, x, y. So this will be a del cross v with respect to y will be equals to del by del z of vx minus, and this will be reverse of this, del by del vz of del x. This is called as a vector cross multiplication. Okay, vector cross multiplication of del operator, del cross v vector, okay, del cross v. So this is del cross v z, again same cycle x y z. So z, after z there will be x y. So this will be del cross v with respect to z will be equals to del by del x of vy minus del by del x of vy. Okay, del y. So this is a scalar multiplication, a del into vector. Okay, del into vector, where we have discussed, here we have discussed del into vector, and this is how del into scalar is operated, and here del cross vector is, this is how it is operated, del cross vector. Then few more. This is clear to everybody? Anybody else, anything to discuss? Just remember as it is. I am telling you, mathematics, I cannot cover mathematics in transport phenomena. So you need to revise everything. So this is just whatever be the information needed for this class, that is only I will revise, and we will use this information in our class. Then this is the del dot. Okay, this is del dot, and that is called as a divergence. Okay, divergence of the vector del dot v. It is called as the divergence of any property. Divergence of any property, del dot v will be equals to variation of that property in x direction with respect to x plus del vy, variation of y property with respect to y plus variation of z property with respect to z, and this is called as a del dot. This is del into, this is del cross, this is del dot. This is a scalar multiplication, this is vector multiplication, and this is divergence. Okay, this is called as a divergence. So this is pronounced as a del into. This is del into scalar or del into vector. Similarly, this is del cross vector or del cross scalar, and this is the del into del dot. Okay, this is del dot, not into, del dot vector. This is called as the divergence of property. This already we have discussed when we were discussing generalized Newton's law of viscosity. Then we have few more property. Velocity dot del cross, not del into scalar. So velocity dot product with a del and into scalar. Okay, that will be equals to velocity x plus d by dx of scalar plus velocity y plus d by dy of scalar plus velocity z d by dz of scalar. This is how we can read velocity dot del into s. Similarly, del cross del square s. Okay, square operation of del into s scalar, that will be equals to del dot del s. And that will be equals to del 2s by del x square plus del 2s by del y square plus del 2s by del z square. Just you keep all these differential operator ready for use. Okay, so most importantly, now remembering this will be very difficult, but remembering this is very easy. So whenever we have this, so we can write this in this format, and we can remember, we can use this very easily, and whenever we need, we can expand into this form and use accordingly. That is the use of this all del scalar multiplication, vector multiplication, divergence, and then this is called as a Laplacian. Okay, Laplacian of the scalar, and all other properties also we will be discussing as whenever that properties are used. Okay, everything is clear. Okay, with this information, and this is the definition of differentiation. Okay, derivatives, so time derivatives. So we can start our discussion. Okay, that is equation of continuity, and then equation of continuity. After that equation of continuity, we will be discussing equation of motion or equation of change. So what is equation of continuity? Is a mass balance equation. Okay, so simplest equation of continuity, you can say what is equation of continuity is a mass balance equation. And what is mass balance equation? How to get mass balance equation? Roll number 1, Abhinav.
Yes, sir. So mass flowing in minus mass flowing out is equal to change of rate of mass.
Yeah, and how about what you are missing? Two terms.
Sir, accumulation and uh, production or regeneration.
Not accumulation. Accumulation will be there.
Consumption and
Okay, consumption and
generation.
generation. Okay, so equation of continuity is mass balance equation without generation and consumption. So rate of mass coming in minus rate of mass going out plus generation of mass plus consumption of mass, that will be equals to accumulation of mass. This will be overall mass balance equation, but in continuity equation, so we will not consider a generation or consumption. Okay, generation without generation and consumption, mass balance equation without generation and consumption is called as the equation of continuity. So what is the concept of continuous flow? Continuous flow, when I can call it as a continuous flow, for a fluid flow to be a continuous, we require that velocity. Okay, so because we are dealing with a continuous flow and momentum transfer, so velocity will be the integral part in a discussion. So with respect to velocity, we will discuss the continuous flow. So for the fluid flow to be a continuous, we require that velocity, which is a function of x, y, z and time, to be a finite and continuous function of x, y, z and time. So it should be continuously defined in all three dimensions x, y, z, and it will be continuously defined with respect to time also, from time t equals to 0 to time t equals to infinity. If I have such a model equation available for my flow, then that flow is called as a continuous. So for a fluid flow to be a continuous, so if I have fluid flow continuous, velocity is a continuous function of x, y, z and time. There should not be any discontinuity in this model equation of velocity. Then only I can call it as a continuous flow. This is the concept of continuous flow. And what is consequences of continuous flow? There are two consequences. No segment of fluid can join or broken apart. Once system is started, once you can say experiment is started at time t equals to 0, if there are two fluids apart, so there will be two model equation discussing these two fluids which are apart moving, maybe in one pipe itself, but they cannot join together after start of the experiment. So this will be consequent. Then if they are joining together and making one fluid, if they are joining together and making one fluid or one phase, then you will violating this continuous flow. Similarly, if you have a continuous flow, so it cannot be broken apart immediately sometime after starting the experiment. Okay, that will be consequences of the continuous flow. And if there is an interface, say there are two fluid moving together and they are immiscible fluid and there is an interface, that interface will be there always. Okay, interface will be there always, or you can reverse this also. If there is a miscible fluid and that you cannot have interface in between sometime after start of the experiment, say water is moving and suddenly there is an interface created, so vapor and water, okay, generally water vapor and water is created, so that will give rise to a discontinuous flow actually. So it has some consequences that we'll discuss. That is, you can say, complicated version of discontinuous flow when water vapor is generated while flowing in a pipe. So this interface, if there is an interface, it will always exist. If there is no interface, then you cannot have interface anywhere after start of experiment. Okay. So this will be the consequences of the continuous flow. And this is the concept of the continuous flow. Velocity will be the continuous function of x, y, z and time. So to discuss this continuous flow, so we will have this equation of continuity. So equation of continuity will be, so this will be rate of mass coming in minus rate of mass going out without generation and consumption. We are not considering any reaction by which mass is consumed or any reaction by which mass is generated. So rate of mass in minus rate of mass out plus this will be accumulation. Rate of mass in minus mass out will be equals to accumulation of mass. Okay, so this will be rate of increase in mass. So how to get rate? How to get rate? Roll number 2, Abhishek.
Yes, sir.
How to get rate? Rate
So
of
it,
mass.
kg per second, the change in mass per second per unit time.
Okay, how to get rate?
So cross sectional area, we can check whether what amount of mass is passing a cross sectional area in unit time.
Okay, okay. So cross sectional area multiplied by
Sir,
how to get rate of mass coming in? How to get rate? Cross sectional area multiplied by
by the thickness and the density.
thickness and
By the
density. Velocity
velocity and density.
density. What is velocity into density?
The velocity into density would be kg per meter square second.
What is that?
Flux.
Yeah,
Flux.
that is. So we will have mass flux coming in my control volume multiplied by cross sectional area minus mass flux going out from my control volume into cross sectional area in all three directions. That will be equals to accumulation. So rate of increase in mass. So mass, how to get mass? So density multiplied by volume will give you mass, and variation of this mass with respect to time, that will give me a rate of increase in mass. So consider a control volume. Okay, consider a control volume at XYZ with a thickness delta X, then delta Y and delta Z. Okay, at XYZ. So this thickness in X direction is delta X, thickness in Y direction is delta Y, and thickness in Z direction is delta Z. So this is my control volume. So I want to discuss this rate of mass coming in this control volume in all three directions. Okay. So rate of mass coming in X direction, rate of mass coming in Y direction, rate of mass coming in Z direction, minus rate of mass going out in X direction, rate of mass going out in Y direction, rate of mass going out in Z direction. So how to say starting first to start with, I will consider X. So X direction. So let us have Vx. Okay, this is the direction, X direction. So I want to discuss the rate of mass in. So how to get this? Say consider Vx is a velocity of molecule in X direction. Velocity of molecules moving in X direction. This is X velocity. So these molecules are moving in X direction with a velocity Vx. Density into Vx. Okay. Density into Vx is a mass flux of molecule in X direction. Mass flux of molecule in X direction and multiplied by cross sectional area. What will be the cross sectional area? This will be a delta Y into delta Z. Okay, delta Y into delta Z is a cross sectional area. Delta Y into delta Z is a flow area. Now mass flux into flow area will be a rate. Okay, mass per unit time, that is the rate. Rate mass change mass per unit time rate. It will be a rho into Vx into delta Y into delta Z, and this arrow indicates rate of mass coming in X direction at X, and this will indicate, this arrow indicate rate of mass going out from a control volume in X direction at X plus delta X. Okay, so this will be a, you can say this is the flux at X, and this will be a flux at X plus delta X. Similarly, this will be a rho into Vx delta Y delta Z at X. This will be a rate of mass coming in X direction. This will be rate of mass going out in X direction. Okay. Similarly for Y direction. What will be for y direction? Roll number 3. Roll number 4, Aditya.
Yes, sir.
What will be for y direction?
So for y direction, the mass flux will be rho into Vy, as we are
Very good.
considering velocity as Vy, and then flow area will be delta x into delta z.
Okay.
So mass per unit time will be rho into Vy into delta x into delta z. And for going in, it
That
will
will
be
be
at
estimated
y.
at y. That
Yes,
will
sir.
be
And for
estimated
going
at
out,
y
it will be
and y
y
plus
plus delta.
delta y. Okay.
Yes, sir.
That is for in y direction. Yeah. 5 Aditya. Roll number 5 Aditya.
Yes, sir.
What will be a rate of mass coming in z direction and going out in z direction?
So in z direction, we'll have velocity Vz. So mass flux will be rho Vz. The flow
Okay.
area will be delta Z into delta X.
No. How delta
Sorry, delta. Yes, sir. Delta Z into delta.
delta z again you are telling in z direction. Flow area in z direction is
Delta X into delta Y. Sorry, sir.
delta x into delta y.
Yeah.
That is
So
estimated at
yes,
z and estimated at z plus delta
Z plus delta. Yes.
So similarly, you will get a rate of mass for y direction and z direction. Roll number 8, Ali.
Yes, sir.
So how to get accumulation?
Sir, accumulation.
Rate of increase in mass for this control volume.
So change in mass.
Change in mass.
Total.
How to get mass of this control volume?
So density into sir volume.
So what is the volume of this differential shell?
So del x into del y into del z.
Okay, del x into del y into del z into rho. That is mass and variation with respect to time. So del by del t of this thing actually. So
Yes.
this will be a del by del t of del x into del y into del z with respect into rho with respect to time. And this control volume is kept constant, so you can keep this del x, del y, del z outside this differential operator. So it will be del x, del y, del z d rho by dt. Okay. So you can substitute. This is rate of increase of mass, and this will be a rate of mass coming in x direction. Similarly, you will get rate of mass coming in y direction. Similarly, you will get rate of mass coming in z direction. And this will be a rate of mass going out in x direction. Similarly, you will get rate of mass going out in y direction, and you will get rate of mass going out in z direction. So substitute everything first of all and write the equation. This equation of continuity. Substitute this and this minus this. Similarly for y direction, this okay in y direction this will be a this minus this phase, and z direction this phase minus this phase. Write the equation of continuity. Substitute everything and write the equation of continuity. So equation of continuity of substituting everything. So this will be a mass coming in x direction minus mass going in x direction. Delta y, delta z is taken constant. Similarly, this is mass coming in y direction, mass going out in y direction. Delta z and delta x is taken constant. This is mass coming in z direction and mass going out in z direction. Delta x, delta y is taken common to this thing. So this will be a rate of mass coming in minus rate of mass going out in all three directions, all phases. And this will be the accumulation of the mass, rate of increase in mass, del x, del y, del z, d rho by dt. Everybody is getting this equation? Here, roll number 9, Nitin.
Yes, sir.
You got this equation?
Yes, sir.
So, what should be done to get the differential equation then?
Sir, dividing by differential volume on both sides.
Yeah, very good. Divide by delta x, delta y, delta z, both side of the equation, and use the definition of differentiation. Because I have property at x and property at x plus delta x. So divide by delta x, delta y, delta z. So this will be a property of x minus property at x plus delta x divided by delta x. This will be property at y minus property at y plus delta y divided, this is delta y divided by delta y. And this is the property at z, and this will be a property at z plus delta z divided by delta z. That will be equals to d rho by dt. So what equation you will get, Nitin?
Yes, sir. D rho by dt equals to dou by dou x of rho into vx plus dou by dou y of rho into vy plus dou by dou z of rho into vz.
Very good. So this is what you will get actually. Divide by delta x, delta y, delta z, and taking delta x, delta y, delta z tends to 0. So dou rho by dou t. Okay, del rho by del t equals to minus. Minus will come actually because this is property at x minus property at x plus delta x. While when you are using the definition of differentiation, it will be x plus delta x minus x. Okay, so there will be minus sign here. Everybody got this minus sign? Nitin?
Yes, sir. Yes, sir.
Okay, so this is dou by dou x rho into vx plus dou by dou y rho into vy plus dou by dou z rho into vz. So this you can say this is the equation of continuity. First form of equation of continuity. Now you will see. So this is equation, okay, but there are 4 terms to remember in this equation. Now here you will see the beauty of mathematics. Now I can rearrange this equation appropriately so that I can write in simplified form so that it will be easier to operate, easier to remember. So this is the equation of continuity. You can say first form of equation of continuity. Here after just a mathematical operation only. Rearranging the equation. Okay, rearranging the equation. So here you can say this is the divergence of rho into V. What is this? A property, x property, variation with respect to x, y property, variation with respect to y, z property, variation with respect to z. So this is the divergence of rho into V. Okay, this is what you can say divergence of rho into V. So d dou by dou t of density will be equals to minus divergence of rho into V. So it is obvious. It is obvious that okay, this equation is very easy to remember. If you remember this equation and if you remember how del dot rho v is operated, so you can get back this equation very easily. This is what the mathematics we will use in this transport phenomena, so that this equation is easier to remember, easier to operate, easier to handle actually. Okay, so dou rho by dou t, del by del t of rho will be equals to minus del dot rho v. Okay, and where del dot rho v is the divergence of rho into v. Where divergence of property equals to dou by dou x of x property, dou by dou y of y property plus dou by del z of z property. Okay, this is what the equation is there. Then for incompressible fluid with constant density, if my density is constant, so this d rho by dt will be equals to 0. My density is constant, so variation of density with respect to time is 0. I can take this out of this differential operator. Okay, I can take out of this differential operator. And so what will be the equation of continuity for compressible flow? So it will be, so this will be 0 and I can take out this density outside this del operator and rearrange the equation. So what equation I will get? Del dot V equals to 0. This is the equation of continuity for incompressible fluid. This is the equation of continuity, generalized equation of continuity, but applied to incompressible fluid. So I can write same equation in this form, del dot V equals to 0. Okay, and this equation already we have used. Okay, so this will be a divergence of velocity will be equals to 0. Okay, divergence of velocity equals to 0. That is also equation of continuity, but that equation of continuity is applicable for incompressible fluid. And this is generalized equation of continuity. For incompressible fluid means density is constant. As density is constant means this d rho by dt equals to 0, and I can take out this density out of this del operator. So after rearranging this equation, I will get this equation, divergence of velocity equals to 0. This is the equation of continuity for incompressible fluids. Okay, so this we have already used. I think almost 10 times we have used in this transport phenomena subject itself. So if you remember, wherever we were getting this generalized Newton's law of viscosity, this second bracket was neglected. Why this second bracket was neglected? Because this is the divergence of velocity, and we were dealing with a continuous flow, and we were dealing with a liquid flow. So wherever in chapter 2, everywhere we are dealing with a liquid flow. Liquid flow means constant density system, and continuous flow. Hence del dot V is taken to be 0, and this generalized Newton's law of viscosity, we have neglected always this term. We have not taken this term in any of the derivation. So we were working with only first term. This is why for liquids incompressible, most of the liquids are incompressible. For incompressible fluid, this del dot V equals to 0, and this already we have used. That is the equation of continuity. Okay, so equation of continuity means I should have continuous model equation for velocity in x, y, z and time. That is, if I have bulk of the fluid or packets moving together, so it will remain as a packet. So interface will be as it is. If there is no interface, interface will not be created at any point of time. Okay, so this is the equation of continuity. So so this is what equation of continuity is there. So I can have some other form of equation of continuity. Okay, so rearranging this equation. Okay, so this is just rearranging this equation. So, and now can you introduce a substantial time derivative here? Introduce substantial time derivative. First, split this using a product rule for differentiation. First property into differentiation of second first property into differential of second property plus second property into differential of first property. Use product rule here to open up this bracket and then rearrange all the term so that you will get a total time derivative, a substantial time derivative. Rearrange this equation, and that is also one form of equation of continuity. So opening up this bracket, okay, so this is what I am telling. Open up this bracket and rearrange so that you will get this equation. Okay, substantial time derivative of density will be equals to rho into del dot V. So open up this bracket. Okay, first open up this bracket. So what we have done, this is the first property into differential of second property plus second property into differential of first property. Similarly, this bracket is also open. Similarly, this bracket is also open. Then rearrange this equation. Now you can see what is this, d rho by dt plus vx d rho by dx plus vy d rho by dy plus vz d rho by dz, and this is nothing but the substantial time derivative of a density. And this rho you can take it constant, and this will be a d. So you can see this. So this will be a substantial time derivative of density rho into del dot p. Okay, so likewise you can arrange. Okay, this is one equation of continuity. So this is the substantial time derivative, and delta is the divergence. So this is one form of equation of continuity. This can be written like a divergence of rho into V, and this will be a substantial time derivative of density plus density into del divergence of velocity equals to 0. That is again a equation of continuity, another form of equation of continuity. So these are the equation of continuity for Cartesian. Now you can see, so the importance of these mathematical operators. Okay, so this is d rho by dt plus divergence of rho into V. What is this? D rho by dt plus divergence of rho into V equals to 0. Now, if you know what is the definition of del operator for cylindrical coordinate system and how del dot is operated in cylindrical coordinate, or how, what is the definition of del divergence, how divergence is operated in cylindrical coordinate. So you will get an equation of continuity in cylindrical coordinate system. Similarly for spherical coordinate system. This is also importance of mathematics. So generally we can operate easily Cartesian coordinate system, and we can get an equation for cylindrical coordinate and spherical coordinate system. So this will be the cylindrical coordinate system. This is the equation of continuity in Cartesian coordinate system which we have derived. Similarly, if you know the definition of del and how del into is operated, so you will get this cylindrical coordinate system. This will be using del definition in spherical coordinate system and using the definition del into rho into V. Okay, divergence of velocity into density, divergence of velocity into density, how it is operated. So this will be a equation of continuity in spherical coordinate system. So whenever we have a Cartesian coordinate system, we will be using this equation. For cylindrical coordinate system, we will be using this continuity equation, and for spherical coordinate system, we will be using this equation. Okay, any difficulty in this equation of continuity? Yeah, roll number 10, Aman.
Yes, sir.
Got it, everything?
Yes, sir.
Okay, so I request all of you to revise all mathematical operator, at least which is discussed in a class. Revise the definition of these mathematical operators. What is del, scalar multiplication, and then del cross, scalar vector multiplication, then divergence, how it is operated, and what is the definition of del operator in spherical coordinate, Cartesian coordinate, and cylindrical coordinate system. That you need to revise. And what is the equation of continuity in Cartesian coordinate system? What is the equation of continuity in cylindrical coordinate system? What is the equation of continuity in spherical coordinate system? This is very, very important when we are discussing equation of change. For simplification, we'll be using this information. All these mathematical operators and equation of continuity will be used for simplifying this equation of change. Anybody has any confusion, any doubt over this equation of continuity? Okay, then thank you. We'll start equation of motion in next class actually. So we'll start this discussion in next class, equation of motion.